Hello, and welcome back to the Handstandcast with me, Emmet Lewis, and my co-host Mikael Christiansen. We have a very special show this evening because we are joined by a guest, a good friend of ours. I will introduce him with his formal title of Dr. Helgi Freyr Rúnarsson from Iceland, who, I don't know, Mikael, how would you describe Helgi?
How I describe Helgi? Oh, well, that is very clear, actually. I would describe Helgi as the ultimate life form because he has several desirable traits. First of all, he is a PhD in physics. He can do a one-arm handstand. He has a wife and 3 kids that he's able to somehow manage in this. And he doesn't drink coffee. Take that in for a good 10 seconds and imagine where you would be without your cup of coffee. I know that I sure as hell wouldn't be any of those things. So welcome, Helgi. Really nice to have you on.
Yeah, thanks for joining us. Thanks for joining us. Helgi's been a good friend of ours for quite some time, so I'm excited to have you on.
Oh, I forgot to say, he's also level 100 in Path of Exile, and that is as fucked up as all of the other things combined.
Okay.
Shit. Yeah.
Greatest achievement.
If you know, you know.
Yeah, so Helgi, why don't you just tell us a bit about yourself and what you do and all these kind of things, just so people get an overview of how the ultimate life form functions day to day.
Yep. Yeah, well, you forgot to mention I'm from Iceland, so that also puts me in a very small pool of people where I'm from, I guess. But yeah, I mean, I'm a 33-year-old from Iceland. You guys have said that I have a physics PhD. I finished that in 2017 in Portugal. I was on numerical solutions of black holes, namely like black holes with hair,
black holes,
whatever that means. I'm not going to go. I'm not going to go into what black holes with hair actually means.
What I want to know is there a black hole comb?
Probably. You know, how far do I go back? I used to play football as a kid. That's kind of how I got introduced to exercise and stuff. But I got very injured around 16 or 17. Basically gave up all exercising, went into studying physics and playing video games, as Mikael mentioned, for about 10, 12 years. Basically didn't do anything else. I studied for 8 to 12 hours a day. The rest of the day was sleeping or playing video games. When did I get in touch with you, Emmet?
It's 2015-ish, maybe 2014, maybe.
Yeah, something. 14. I think that's the time when you helped me with my back bend, because basically after this huge injury, I didn't move at all. But then I started exercising again via some like random boot camp classes, yoga stuff. And yeah, I met you on Reddit, I think, 2014, 2015 maybe. And you were like beta testing all your programs of like back bending and head to toe and stuff. And it worked for me. So I said, I'm not going to do yoga anymore. I'm going to do what this guy Emmet is doing. And I kind of started focusing on handstands. At that point, that's how I got to know Mikael, I think. I think it's actually quite funny because like when I met you the first time, Emmet, in Berlin, I think you had just come back from the workshop with Mikael when you were meeting him for the first time. I think it was like a week or two later or something. Like I was meeting Emmet it was very. Then I somehow transitioned from training with you, I think over to training with Mikael.
You were like, and then, I don't really want to train flexibility or strength and conditioning or anything else. I just want to do handstands. So I'm going to train with Mikael. He does Path of Exile. I was like, have fun. Off you go.
Yeah. Well, we didn't. I didn't know Mikael played Path of Exile. I would have left a long time before.
Yeah,
if I had known
first time I came to Iceland, we were sitting there talking like because I was teaching you a workshop in Iceland. First time I actually met Helgi, and we go to his place, drive the quite a long drive from the airport. And we were speaking about like being like enthusiasm and stuff. I remember, and I said like I was so hyped about this new patch for this new game, and he's like, "Wait a second, what game is that?" I was like, it's this obscure like small indie company from New Zealand. It's called Path of Exile." And he's like, "Do you play Path of Exile?" And then like he just slams my face with like, "Yeah, he plays hardcore and like all these like obscure build solutions I've never heard of." Like, shit, this guy knows what he's talking about.
So what you're getting is like a glimpse of our conversation when these two are around. I don't play Path of Exile. They've been trying to make me play, but I hold off because it's not really like a game I like. And Yeah, it's just obscure builds, types of Path of Exile, and
Running
how
maps,
Helgi
doing the
running
thing
maps
over and
and
over.
Yeah.
staying up to 5 a.m. to run maps when they should be sleeping.
But yeah, so why
Yeah.
are you with us today?
But well, it's not
It's
for
not.
Path of
It
Exile
could
for
be.
sure, but well, it could be for sure. But we were going to talk about some like physics related stuff in relation to the handstand. Kind of I don't even remember the first conversation me and Emmet had about it, but you know, since I'm a physicist, and I mean, Emmet technically did some
I
time
didn't
in the
finish
physics
it though, but
department.
I haven't
at
got my
least.
doctorate, but I
No,
spent some time.
Yeah, the idea is kind of like to go through a bit like in a physics sense what it means to balance on your hands and like stuff about levers, basically the questions you guys have.
Yeah.
And you know,
I've got
whatever.
some stuff I've been
We'll spin
brushing
it,
up on
I guess.
research the last couple of weeks as well for this, because I think it's I don't know, it's a very interesting topic, particularly because like there's one of the things I've realized is the terminology, and we're partly responsible for this because we use a very dumbed down terminology, and then it's not actually what's going on, and now people are not understanding. It's like, you know, it's like all these examples in most maths and physics stuff. It's like we use a simplified thing just to explain it so you grasp the idea, and then but that's not really it. It's like, you know, ignore friction because friction doesn't exist in the model but actually exists in real world.
Yeah, like the first thing that strikes me then is like the perhaps most talked about thing that that has to do with handstand, and that is the line. I mean, that as kind of a phenomenon of physics does not express as it might seem that it does in kind of the intuitive sense of looking at the body line and then imagining that, oh, everything is stacked up on top of each other. That must make it easier, just as a brick that, or if you stack bricks on top of each other, they will stay more nicely in one configuration than another. But there are kind of different, or that there are differences between these static objects and our like fluid-filled bodies.
Yeah, for sure. I mean, because the thing that people think about, I think, the first time when they hear like a straight line in a handstand is like, especially in like a mathematics or a physics kind of sense, is that everything should be at 180 degrees. Oh, your hips should be fully extended to 180 degrees. Your knees should be fully extended, your ankles, your shoulders, and that will make you hold the straight line. While, as you guys have talked about in the podcast, is that is not strictly true. Like for like what you call the mechanical line, Mikael. That's not the definition of that. But people seem to aim for that because that is what straight kind of means in this mathematical sense. That people latch onto that, and I think that's a big part of the confusion because people think straight in the maths kind of sense, while straight can mean something completely different.
I think.
Like in terms of
I was
balance.
wondering actually if you could explain for people the difference between the center of mass and the center of gravity.
Suffer.
I mean,
The
you
official,
mean the official
just
difference?
Give us an idea, because like from my understanding of it and physics understanding, is the center of mass is basically a fixed location in an object when the mass coincides. Now the center of gravity is actually if we were to break your body up into individual points and project a line from that point to the center of the next gravitational body, correct me if I'm wrong now, so that would be the center of the Earth for all intents and purposes here, you would do an equation that would sum up the locations of all these points and find out where they all coincide or where their cumulative center is. And this can move around because by the way we deform the body, it can be like even outside the body, I suppose.
Yeah, and and it's this idea that, like, I mean, you might remember this, but when we're talking in physics, and especially like Newtonian physics, we talk a lot about like point masses, as in we say we can model a body that has a mass by one point. We don't actually need to know its shape. We just need to know its center, kind of like how Kepler derived his laws of planetary motion. He's not considering that the sun is made out of a lot of atoms. It's just a point mass at a certain distance. And because those objects are basically spherical, essentially. There's some deformation, but it's very small. The center of mass and the center of gravity are in the same place because they aren't deformed. But like for the human body, you can say if the center of mass is, and I mean, I'm not quoting you, Mikael, but you say this very often, that it's around your navel. Like it's slightly beneath your navel or something like that. But as soon as you pike, as soon as you do something else, it actually goes out. I mean, your center of gravity then will go outside your body. Which doesn't make any sense if you actually think about it. Like if you're thinking about center of mass, but center of mass isn't the same as center of gravity, because center of gravity is more like if you would model your complicated structure as a point object and how gravity affects it, then that's the point where it would be, in a sense. That like because obviously it's very hard to calculate anything from a complex shape. No, I mean it's this thing. It's the only thing I knew that I was going to say on this podcast. Is there's this thing that I was told while I was studying that it's a story about how physicists work, and it's basically, I think there were physicists in the UK were asked to calculate greenhouse gas emissions from cows in the UK or something, and they wrote a huge paper on it. You know, every like I don't know how many pages, but it started with the assumptions of this paper are that we have cows that are spherical in a vacuum. because it simplifies everything. Because like as soon as you so they somehow simulated or did something for, you know, the process of greenhouse emissions, and it helped that they would be spherical in a vacuum. And that's the same thing you have to do for almost everything. You have to make some simplification such that you can actually do math. That is almost the problem of physics. So a lot of things that we do have to be very like idealized. They have to be like, oh my God. Yeah, idealized basically in the sense that they don't really represent anything in the physical world anymore. But they will still give us pretty good ideas of how things work. Even my PhD had a assumption like this. So, you know,
they have.
Well, they can, but the hair that I was studying doesn't describe any physical particles.
Essentially a wig.
So hair.
A wig.
No, we're not going to go.
But so like what it made me think, like in terms of that with center of gravity, and I've like always been wondering. I'm really happy to get that cleared up, like the kind of some sort of at least useful distinction between center of mass and center of gravity, because I've even heard the terms thrown around interchangeably, or even as if center of gravity doesn't exist as a term. Yeah. Obviously it does, but what it makes me think, just like a random thought, because obviously I'm aware of when you're doing like a pike handstand, say shape such as a pike handstand or a figa or so on, like that point will sort of be outside of your body, that kind of
the center of mass point.
Or like so, and the interesting feeling when doing that, and I'm sure like both of you can really easily relate to this, is when you do a good pike and that point is above your hands or above the middle of your hands, you're never feeling that you need to go excessively over your fingers, because like that point is not actually moving over your fingers, even though your ass is technically past your finger point. And this is like the thing that I've been demonstrating several times as well, with like the fingerless press and the fingerless pike handstand and so on, where it never actually moves outside. But whereas if you move your shoulders forwards excessively in the same type of pike, then you're actually moving that point forwards, hence putting more pressure and strain over your wrists.
But just to kind of reiterate the point of how physicists work, like if you go to Wikipedia and type in center of gravity, or actually you find it on the article for center of mass, there's a subsection for center of gravity. It just starts with a body's center of gravity is the point around which the resultant torque due to gravity forces vanishes, which doesn't really tell you anything with like how it actually works. But it's also a problem with, because
I'm not going to say that's too complicated. We'll leave that one as an exercise to the reader.
We could go on for a long time.
I have a concrete question, because this was, I remember I asked you this in the lead up to us doing this podcast, and like just in terms of how to say, since I guess for a lot of our listeners too, like a lot of the lingo in this is a bit kind of abstract and obscure. But one thing that I've been thinking a lot about is like how to define, for example, our various body parts in a handstand, and then particularly maybe in a straddle or even more in a one-arm handstand and so on. But I asked you about a specific term. I can't remember what I was using. Maybe it was like, maybe I was talking about the radius of a circle, and you called it the lever. And I'm from my understanding, the lever is kind of a useful term in terms of determining your extremities of the body. Am I correct? Something?
Yeah, I mean, basically the lever is just describing it. Also, it's not just thinking about the length away from the center of your body, kind of, which is what the radius length or radius would imply. But the lever is actually telling you, okay, so it's applying more force. There's going to be more torque, like due to the length of the lever. So it describes the difference between saying a tuck or a diamond or a straddle, because then you're putting more mass further away from your center, basically, which creates a larger lever. And I like, easiest way to describe it is just a seesaw. If a seesaw is very short, it's going to have different forces than a seesaw that is very long. And if a fat kid sits on the end of a seesaw and a light kid sits on the other end, there's a very different force at play. And most kids will do this. Like if you watch them at the kindergarten, I don't know if you have seesaws everywhere in the world, but you can still balance it by moving the kids to a different part of the seesaw, and then they will actually have the same amount of torque on the seesaw. So that's kind of the idea, and why we call it a lever rather than just the length of the. I mean, obviously the lever has a length, and that plays a huge role, but also the mass on that lever. So
I think it comes down to, like, here's an interesting thing on the modeling side of these things, that because our legs have mass at every individual segment. If you imagine we slice it into slices, each bit of that is acting on the length of the lever. Whereas if you imagine a kid and a plank, and the plank is basically the weight is inconsistent with the weight of the kid at either end, you get this leverage force. I was just wondering, it kind of goes to this point of, with the levers and say the straddle and the changing of the center of mass, is there any way we could calculate that meaningfully, that I could go, if I bring my legs into
a vacuum?
Yeah, so we'd start with a circular hand balancer in a vacuum with completely uniform thickness legs of length L on each side. So then can we work out, if the legs are up overhead, how high that raises the center mass compared to, say, when they're in a full straddle, which they have a perfect 180.
Yeah. I mean, you can calculate it, and the way that so like we talked about this a bit, and I kind of looked at, especially for straddle, because that's the easiest case. But the problem with physics, again, is that you always have to make assumptions. And the first assumption that you have to do with something like this is that the upper body, so from your hips and then up, down to your fingers in a handstand, remains absolutely still.
Yeah.
It has to. So you're kind of doing an open straddle. Don't pike is essentially the assumption that I did. And then it's very simple. Like, the center of mass of your legs is reduced by like the cosine of half the angle of your straddle or something, which is like cosine of an angle goes between 0 and 1 essentially. So you can reduce the center of mass of your legs, so not the whole body, obviously. But the thing is then that the center of mass of your whole body is then just a combination of these two things, and it's very simple. If you look at, like, if you just Google center of mass, I think one of the first images is like the center of mass of 2-point objects. So the assumption that you have to make is that your upper body is 1-point object and your lower body is 1-point object. The upper body doesn't change, so the center of mass of your lower body will then lower a bit, which will obviously lower the total a tiny bit. But it's very hard to say just like, oh my God, you straddled 45 degrees and that means that it lowered by 10 centimeters. It obviously depends on the weight ratios of your upper and lower body. There are some relations, but they're all quite intuitive. I guess, in a sense. Like if your legs are light, then your center of mass will not move as much.
What you're saying now, if the legs were longer, would that mean the center of mass would move more?
No, technically not, because it's only the angle between the legs that matters, and the like assuming fixed weight. The weight is always going to be the biggest like part, kind of.
So because if you would want to calculate the weight per centimeter of a leg, that things would start getting really, really, really complicated, I would assume.
I don't know. You could get out like a meat slicer and do it.
You can technically do it, but the thing is like, and we looked at some papers before of like weight distributions through the body and stuff, and like most of the like a lot of the weight of our body is in our trunk.
Yeah.
So your center of mass isn't actually moving. I mean, it's moving something. I don't like you can easily plug in some numbers and see if it like for a so and so high person it will move like so and so many centimeters. You can easily do that, but it's going to be different for everyone, obviously, depending on different straddles and stuff. What I find interesting though is that like a deep tuck can lower it even more, because you can get your knees below your hip line. So that was like the first thing I noticed, because but that's the thing. Then you have to pike your hips, which we didn't allow you to do in the straddle. So
for like the equivalent for a deep tuck in a straddle would basically be somewhere in a press to handstand and in angle wise.
Basically you're down. Yeah. So, and the thing is too, is that the levers almost stop mattering since you're on two arms, because they always balance each other out. So like a diamond and a straddle, it doesn't change any forces to the side because they balance each other out.
Like there's something interesting though, like you said there, I thought to mention as well before, is that like, as we all know, all of like the practicality of standing on your hands becomes drastically more complicated when you take away an arm, and I guess we're going to get into that as we go along with the discussion, since there's becomes a lot more forces that apply and so on, and things I don't understand. But
before we get onto the one arm stuff,
I have a point.
Cool. I got some stuff about
several
two arms
points with two arms before we go there. But
you can see we're prepared.
Like what I find very interesting is like, let us say we continue down from the deep tuck, or let's now say like we're going go from handstand, or the leg straddle, the legs start going down towards a press to handstand, and at some point like the legs will start passing inside of the line of the arms, and you're essentially starting to do a Stalder negative press, right? So you're starting to approach the straddle L position, and from what I have understood from my purely intuitive understanding is that like when you're sitting in a straddle L, kind of, then your center of gravity is somewhere around your sternum, and like as you're going down deep enough, because either when you lower yourself down, you stay with your hips extended and you plunge, which leads to that massive angle. But if you pike a lot, you're reducing that angle so significantly, because at the point where you would need to go significantly forwards, the legs actually come inside of your arms and start counterbalancing your ass and so on. And what I found with the straddle L, and the reason I mentioned this is that there is a spotting technique that I use for spotting the straddle L's. I think I've done it on you, Helgi, when you start in the straddle line, and I grab by the sternum rather than by the hip in the beginning, and it seems to make sense to help the person from where their actual center resides, rather than pulling from the hip in that point. So it does seem to be that like, since you're so compressed in the body, that your center actually goes up a significant amount.
Yeah, I mean, if we just think about it almost from the other direction, like when you're standing on your feet, where is your center of mass or gravity? It's around your navel. Now you moved your legs up to your hip level. That means that your center of mass or gravity is going to go up. So it's definitely going to be higher than your hips. Is it at the sternum? I don't know, because it depends for every person. Like how much do they flex their spine? How high can they push the floor away? You know, all that stuff, and how high do they actively pancake? But yeah, it's definitely higher than your belly
Probably come a
button,
bit
I
further
guess.
forward as well because
How
you've got
high?
the piking at the hip.
That's the thing. It's So I think that also helps as well because it's now a bit more forward. And if you're like what people usually do is they will grab like behind your thighs, under your thighs, almost over your head, kind of, which means that you're grabbing like super far away from this point. But if you're grabbing around the sternum and kind of around the ribs, then you are kind of lifting that point, which means that if that point's lift, then you can maneuver the legs better, I guess.
Not get lifted, basically. Because like the butt lift, like it's one of those ones like
you just
and the thing is, if you grab on the behind, if you grab behind the thighs and pull, what is going to happen is you're going to apply forwards force as well. So unless you block their knees, you're literally sending them into a forwards roll because there's no way your forearms and your fingers can handle that much extra force when your shoulders are already front.
Yeah, it's definitely like that butt lift way of spotting a shoulder is like the worst thing I've ever seen.
It doesn't seem to do much. Like I've seen people do 10, 15 reps of spotted ones of those. Like, are we talking for like very long periods of time in circus school, and then you ask them to do like a slow lower down, and like they collapse at around like when the feet have come inside the arms. It's very evident to me that like this isn't one person I've seen at least 4 or 5 cases. So it does seem to be that like you're not getting to do that work because again shoulders are being blocked and then you're being pulled like away from your center rather than having to what did you say, maneuver around your center.
No, I think especially the lower down to straddle, like you were describing, or straddle L-sit, is it's a very nice way of thinking about the lever stuff. Because like you said, the better your pike, the better your pancake is, the less you have to lean. Because if you're not piking properly, your lever out to the side then of your legs is going to be longer. Your legs still weigh the same, but because they're further to the side, then something has to counterbalance on the other side, creating a larger lever on that side.
It's interesting, like you mentioned that when you said that now, I got this mental image in my head of things I've seen several times. Someone stands in a handstand, they go pike handstand, and they start lowering down towards the floor, but instead of getting their legs close to their body, the legs stop quite far away, and then as they are going to go into the straddle L, it looks as if they kind of do this large swing down into the, into the L-sit, I mean. So it becomes this large swing into the L-sit, and this one, like if done to a straddle L, you usually fall in your ass and backwards. And if done to a straddle L, you kind of end up as if in some sort of bad parallel bar swing at the bottom, where like your ass rocks back and forth simply. And I guess then like you'd have to kind of have lots more of that planche strength to be able to deal with the lever that is further out.
Yeah.
Cool. Yeah. Right, I've got a question or an explanation for people. Can you explain to people what an inverted pendulum is and how you balance one? And how that relates to human bodies.
Sure.
Good one.
Sure. An inverted pendulum is literally what it sounds like. It's a pendulum that is upside down, and I love it because again, this is such a physics thing when you think about this problem, because the pendulum is one of it's the first harmonic oscillator that physicists learn about, which is a very nice way of saying that it's a very solvable problem. Like it's a differential equation that describes motion of a thing. And basically everything in quantum mechanics is usually reduced down to a harmonic oscillator. So it's one of the first things people learn about in physics. And it's like, you're going to be using this for the next 20 years if you're a physicist. And it's completely true. We try to reduce everything to like a harmonic oscillator, which we learn about in the pendulum. So when you start looking at the inverted pendulum and how, it's all pendulums all the way down, like vibration of atom. But it's very funny the way that they describe the inverted pendulum. It's just like, it's just like a pendulum, but gravity is inversed.
Ooh.
Shit.
If you think about it, like, okay, so you take a pendulum and it's fixed at the top and it's swinging at the bottom. Okay, imagine that gravity is now not going down, but it's going up. Okay, now it's an inverted pendulum. So the equations that describe it are basically the same as a normal pendulum. There's just a minus sign there. And then you can just solve those differential equations, and you will see that they give you some some things, how it moves and everything. But the first thing that you notice, because a normal pendulum is stable, which basically means that basically no matter what you do to it, it will either just keep on swinging back and forth, or it will find kind of, if it has some resistance in the system, it will find its the equilibrium point at the bottom. Inverted pendulum is the complete opposite, in the sense that it's unstable. Basically, you can't make it stay upright without doing something, is basically the thing. And it's very nice, because if you read about it, you'll basically find that there's 4 ways, I think, to balance an inverted pendulum, which they describe as moving the pivot point. The pivot point is basically the point where it's fixed at the bottom. And if we think about handstands, that's walking on your hands, essentially, which isn't really balancing it, but if we think about it, it still describes it in that way. So you can find this on YouTube and everywhere. If you if you type in balancing an inverted pendulum, you will see small robots that are balancing wine glasses on big sticks or something, by driving back and forth, and they can balance these things super well. And Raspberry Pi, buy a Raspberry Pi and program it. I think it's easy.
That is basically balance. It's basically how you balance on rings too. That is what you do. You move the ring underneath you constantly.
Yeah. And hand to hand, it's very Then you can basically apply torque at the pivot point, which is what we do as hand balancers. It's using your wrists and fingers and forearms to apply torque at the pivot point, such that you do not fall. Problem with us is obviously that we cannot apply torque. We can only apply torque in one direction with our hands. And then comes the third one, which is, again, physics speak. You say it like this: changing the rate of rotation of a mass mounted on the pendulum on an axis parallel to the pivot axis. That is.
Oh, it makes total sense. I do that all the time in my handstand.
Yeah. No, but it's basically saying that the pendulum is rotating as in its swing back and forth or something, and you apply a force that is perpendicular to the axis of the pendulum. So you move a mass on the pendulum either to the left or right, which is piking your hips, closing your shoulders, bending your knees, doing something like that. You're moving a mass to the left or right in order to balance it. So again, it's just like balancing a handstand. And the last one, which is, it's maybe you don't think about it that way, but you oscillate the pivot point up and down, which means that you take the bottom of the pendulum and you move it up and down, which is kind of what a lot of beginners do. And at least in what I see, is that they will continuously drop their shoulders, elevate their shoulders, drop their shoulders, elevate their shoulders. So you see this in people that can't hold their elevation. They'll be going up and down, up and down, up and down. And then they've kind of changed their pivot point from their hands to their shoulders. And it's called the Kapitsa's pendulum, from probably a Russian.
Yeah, this is the one that you can do. You can do various strange experiments where you kind of shake something and it stays upright. Yeah. You get a drill saw.
I think it was a jigsaw, the experiment you showed me.
But in Iceland, So you basically tie a stick to a drill saw, and then you make it punch up and down really fast, and you can balance a stick upside down that way. And this is, again, from circus, I've seen you do this, Emmet, with a bundle of sticks, holding it in your hand and balancing them. And obviously you will move them back and forwards, but sometimes you will also move them up and down.
Sorry, go on.
But I have one more thing to say, because I think this is the best thing, because we were talking about doing this podcast, and I went to the research mode and I looked at this and oh my, this makes perfect sense for the handstand. The 4 ways to balance an inverted pendulum is just like the handstand. Oh my God, this is just the same. And then at the bottom of the Wikipedia article for the inverted pendulum, it says types of inverted pendulum. And it basically says, arguably the most prevalent example of a stabilized inverted pendulum is a human being.
Roasted.
Because on our feet, everything that I just said about a handstand also applies. So going back to like one of your first YouTube videos, Emmet, how using your hands as feet, it's the same thing.
Yeah.
So, you know, which is great though. I mean, it means we're on the right path.
It's kind of interesting that you basically described in physics terms. Now we're missing one kind of thing relating to the one-arm handstand, which I'll talk about in a second. We basically described in physics terms like all the strategies you will see to people to balance and how they occur. Now there's one thing I want to do a bit of maths nerds or nerd maths or something here. You have to correct me if I'm right or wrong, because it leads into something else. So I can remember when you're working out the physics of a simple pendulum or a simple harmonic motion, that when you are calculating small angle swings of less than 15 degrees, I think, because sine 15 degrees is negligible, you don't have to... it doesn't translate to horizontal. I was looking at this thinking that if we start exceeding 15 degrees of balance correction, that's when we need to actually do one of these either line break corrections or stepping. So we need that. So you could actually probably figure out, like, because we have this kind of model in one of the programs, I think it's in Push Harder, where we're talking about like this type of correction you'll need to do relative to your kind of stability. And it kind of goes like, obviously, if you're super balanced, then your correction is just happening at your finger levers, because that's applying leverage to the center of mass. As you lean further forward, then your options are either to apply more force, but if you exceed the force, you can't, or your line of gravity gets too close to the edge. Then you have to do a line break. But I'm wondering if it gets to about 15 degrees, is it every 15 degrees the horizontal force becomes...
No, so I'm gonna refresh your memory. No, it's basically because you can, in mathematics, you can do something called the Taylor series expansion of any function. So basically the thing is that, which means that you can take a function like the sine of something and you can expand it into what's called a power series, which just means that if you have like sine of some angle, the power series is basically like the angle to the power of 0 plus angle power of 1 plus angle power of 2 with some coefficients in front. Which means that if the angle is very, very small, the angle to the power of 2 is also very small. The angle to the power of 3 is even smaller, which means that for small angles, the sine of something is very small. So you can skip like the rest of the series. So you can basically say that for small angles, the sine of an angle is equal to the angle, basically, is the assumption that people can make. I'm not sure if this translates over to the corrections, like which ones you would be using. I think that's more to do with just like how much torque can you generate at your hands. Because imagine building a pendulum that has a motor at the pivot point that can generate infinite force. And then it can technically rebalance itself from any angle. Problem is we
Mikael
can't. So
not really.
Mikael can't, but the rest of us, not a Mexican though, he can't. No.
That's for you, Helgi. But yeah, like this makes me. Because I've heard these terms before, and I've discussed this a bit with Emmet the last period, but it's interesting kind of to think about, like, basically my brain went through loads of kind of this is a bit of a tangent, but like it's funny because like I don't have any balance memories because I just go up there and do things, right? So like it is like you don't need to remember how to bike, so it's kind of weird to think back and it's like the response mechanisms that I do when I do the various things, they involve all of these possibly several times per second, except the one that like I don't actually move my hand underneath myself, so that one is excluded unless I walk on my hands or hop on my hands or so on. But even that, I remember like when I do a lot of switches, I will often have, for example, this response. I jump to my left hand and I'm off. I'm going to fall, but like I have weight there for a split second, so I just push and I go back to the other hand and reestablish, just because like I wasn't actually in balance. So like, okay, I'll just sort it out by you push off, you travel the force to the other side and you reestablish. But all of these things in terms of the inverted pendulum will kind of be applied at any given moment. But it's also very interesting, as you said, with the fact that the levers have very little to say in a 2-arm handstand, as there is like the lateral forces are virtually negligible, since you're by definition, at least you're, if you were a circular hand balancer in a vacuum, you would be opening your legs exactly at the same time, exactly to the same at the same speed. But even in practice, the differential between that opening will be negligible, since your balancing system and muscles are quite fast and strong.
Yep. There's one. I mean, the thing with Emmet's question from before, though, is that you could obviously calculate this. You could almost. I mean, it should be relatively simple to calculate how much force you can produce with your fingers, just by doing a handstand on a scale and then pushing down with your fingers, like doing toe pulls on a scale, basically.
Yeah, we have some scale experiments in the works. Say that.
Yeah. No, but then you could basically calculate the maximum angle that you can save yourself from.
Interesting.
Like, I mean, is that relevant? I don't know. But you could do it, I think. Like if you think about your body remains a straight line as you're falling over, when can you not save yourself? And when do you have to do something other than just pushing with your fingers? And there might be some general-ish rule. I don't know though. I mean, because clearly you guys have taught a lot of people. I've taught some people. There is like a breaking point for most people, absolutely. No matter how strong you are in your fingers. And it seems to be about at the same place once people have trained it. So there probably is some relation to it, but it's more related to like how tall you are, how heavy you are, and how strong you are in your fingers.
I remember there was this dude when I taught in Australia. Like he was fucking stacked. He was enormous of a man, like a muscle monster. He must have been nearly 2 meters, and he had great shoulders, super good mobility and everything.
Was
and
it
the guy
Thor?
Huh?
Was it Thor?
Don't remember. Not that Thor. But at least like everyone was like, damn, yeah, you should be able to handstand because he's so strong, and mobile and all, and he had good technique, but he just couldn't. And I just took a look at the guy, and I had him try toe pulls, and I was like, it's really obvious, like with the amount of mass that man had, like the amount of force he would have to produce in his hand to be able to balance, like it would actually take him work, just because like he was bodybuilder sized everywhere, and he was extremely tall. So obviously that just equates to for him it would literally just take more hand work than for 95% of people.
Yeah, there's one thing that I want to wrap up the inverted pendulum thing by one, just quoting Wikipedia like I've been doing.
What a scam!
Basically,
You're not meant to
they
quote
derive
Wikipedia in
like
your research papers. You have to copy the references at the end and put them in.
Yeah. No, but it's simple. They basically write down the like displacement acceleration from the central position in terms of the length and gravitational acceleration, and like the initial displacement. So they basically say that like, okay, so if you lean to the right by 1 degree, this is how fast you will start to accelerate to the right. That's basically the idea. That's basically what the equation says. And what the equation says is that this acceleration is inversely proportional to the length of the pendulum, which means that tall pendulums fall more slowly than short ones. Because like throughout this whole thing of like body weight fitness and everything, it's always like, it's harder to be tall when doing body weight stuff because the levers are longer. But in the case of the straight handstand, you actually fall more slowly.
From the top point. That is certainly true.
Yeah, from the yeah.
But you require more force to save yourself.
So
so you basically just have a slower fall.
That's the thing. That's the thing.
But then you just feel you're falling, but you can't save yourself because your fingers are too weak.
Yeah. So it's obviously just like a tongue-in-cheek thing that I want to put out because I'm not tall.
That explains why Tom and Ulrich are so good.
Yeah,
Yeah, that's what I'm saying. It's like it's very clear
but
now.
it's certainly now I completely lost my train of thought, so forget about it.
I have a question that I've just thought of and not mentally prepared for the last week or two. So I was wondering if we could talk about rotation in the one-arm handstand and how we can transfer the moment of inertia and the length of the lever and how that actually speeds up the rate of rotation.
Perhaps.
Yep. I mean, basically, like when things are rotating, it's in physics terms, it's described by something called the angular momentum, which is basically just the rotational equivalent of momentum, which most people kind of know what is. Probably wouldn't be able to give you a definition, but people kind of realize what momentum is. It's a bit more complicated when you're rotating. There's a simple equation for it, and it has to do with something called the moment of inertia and then the angular speed. The angular speed is basically just how fast do you move, either degrees per second or radians per second. Or it's basically just how fast do you rotate, but not in terms of like radians per second. It's like no degrees here. But the moment of inertia is more complex. So it's very similar to momentum. So angular momentum is very similar to normal momentum or linear momentum in the sense that it's some kind of mass or inertia times some kind of speed or velocity. But the moment of inertia is obviously tied to the mass of the object, but it's also tied to its shape, to its levers, and to everything. And you can calculate the moment of inertia for a lot of things, for a sphere, for a cylinder, for just a thin lever, like a lot of things. But what you basically find is that the further the mass is displaced from the axis of rotation, the more moment of inertia it has, which means that it's gonna basically slow it down, which most people kind of know. There's a lot of playground toys that actually kind of exploit this thing, is that they actually have this right outside my house and my kids play on it, where it's basically just a stick coming out of the ground on a platform that spins. So the kids will go on it and then they'll start kicking the ground next to it and they will start spinning very fast. And then it's basically they will shoot either out a leg or an arm and that will slow them down. And then they'll pull it in and they'll start spinning faster. And I've seen hand balancing acts on two arms that do this.
Yeah,
Nicholas. He's been doing it on a spinning table, and it's very clear when you see him doing it there, in the sense that he goes up, he starts spinning, and he will usually start in a straddle. He'll go for a tuck, then he'll extend one leg to straight, and then he'll extend both legs to straight, and he just keeps spinning faster and faster and faster.
Yeah.
Even though there's friction in the actual spinning table, it doesn't matter because he's basically changing his moment of inertia by deforming the shape his body is in.
That's actually quite an interesting video that people will put it into the notes for people to check out. But it's kind of, we think of the difference between a straight one-arm handstand and a straddle one-arm handstand, and we just think of the rate of rotation. It's one of these things me and Mikael have been working to get into the public consciousness, is when you feel stable on two arms and you're doing a 4-finger support or one-arm support or one-finger support or something like this in a straight handstand, it feels stable just because it's rotating so fast that you can't feel the rotation. And if you look at this video, because I know this act you're talking about, I can think about when he puts his legs together when he's going fast, it just basically the rate of rotation almost triples or quadruples.
Even people will probably know this example more. Look at a figure skater.
Or head spins.
What do they do?
Yeah.
Or a head spin, or basically any spinning moment. Like my physics teacher in high school did this with us. He would he brought dumbbells to class, and he would go on his chair off his chair that could spin, and he would start spinning, and then he would extend his arms with a couple of kilo dumbbells in each arm, and he would slow down, and then he would pull it in, and he would speed up again. And by the way, he was like 75.
I thought you were going to say like he was 75
was
kilos
very
of just pure
interesting,
biceps. He would sit there curling during class.
No.
Going, Newton was right.
But basically why this happens is because something like this angular momentum quantity, it's a conserved quantity in a closed system in the sense that it doesn't actually change. So angular momentum is, like I said before, it's the product of the moment of inertia and the angular velocity, which means that if that product has to be the same number no matter what the moment of inertia is, then if you decrease the moment of inertia, the speed has to increase. And then if you increase the moment of inertia, then the speed has to decrease. So it's basically just like two numbers have to equal the same number when you multiply them together. So if you change one, then the other one has to change in the opposite direction. That's basically just what's happening. Why is conservation of angular momentum a thing?
Newton.
Well, I mean, we would need more. We will need a new
Just want to explain
podcast
Newton's
for that,
laws of motion.
But
Angles in.
it's very obvious also in the terms of if we apply it directly, like you said, to a one-arm handstand, and the classical difference between how much harder a straddle one arm and a legs together one arm is. Like Helgi right here, he can actually do a legs together one arm as well, but you know how much longer it took you to get that from the point of being able to do the straddle. And like that is the thing that like you will see it even among professional hand balancers, that like if they do a legs together one arm and something goes south, the first thing they will do is open the legs. Then what is it, increasing the moment of inertia? Is that then the correct term?
Yeah, increasing the moment of inertia, which in turn, because of conservation of angular momentum, will decrease the angular velocity.
It's interesting because as this happens, and like when people are learning this, and as you said, Emmet, that when you're doing, like, because people so often say to me, yeah, but like in straddle I rotate, and how do you fix rotation? And like the idea that I get is that like the reason you are speaking about rotation in a straddle is because you actually feel it happening. It goes slow. You
like feel it on your legs.
Fall out and it happens.
That's
Whereas
the thing.
In with legs together, you might be in like a straight arm support and everything is fine. You take off your hand and you fall, but you don't really feel any rotation because it happens so quickly that you're destabilized immediately.
Yeah. But it's also going back to the levers. Like a lever in a straight handstand, it's very short. It's basically the radius of your thigh, or like it's the length, it's the thickness of your thighs, essentially. It's your lever, like that's your cylinder that is rotating. So so it's not going to move very fast, even though it is rotating fast. So it's faster rotation in the angular velocity sense. It's more radians per second. But in a straddle handstand, because now you've extended your legs all the way to the side, I don't know how many, like a meter or something, depending on how tall you are. So your foot is going to move faster in meters per second, but it's not moving faster in radians per second. So its angular velocity is slower, but you feel like it's going faster because it technically is in like a spatial sense, but the rotation is still less.
That just made it.
Yeah. So let's put it this way: like in a straight handstand compared to a straddle handstand, your butt cheeks are rotating faster in a straight one, because they're in the same place, right? But your leg is in a different place. I'm just thinking it's like so your torso will rotate slower in a straddle.
Yeah,
so that's kind of the idea.
It kind of makes sense if you think of I'm trying to think of the example a physics teacher gave, or one of the physics things. It was like if you have an ant and you have two ants, and one of them is walking around the very center of a pizza, and the other one's walking around the outside of the pizza, and they have to finish at the same time. Yeah. So the one on the outside has to go super fast, even though they're still rotating at the same time. So
basically it's the same thing. So the rotation in a straight one is going to be faster because the moment of inertia is smaller, but the feeling, you don't feel that kind of rotation as much in your body. So you feel like in the straddle, like, oh my God, my leg moved to the front or to the back, and that's what you feel. But you don't really feel well, you do later, I mean, I can say that when I do a bad setup of a straight one arm now, I can actually feel that I am rotating, but that took like a year to actually start feeling compared to the straddle. So
there's this one example and a little physics experiment that you all can do at home right now. So that I
Grab some
like.
bleach.
Basically, I've used this as an example before as well, but this one is very specific in terms of these this rotation and also the to speak about the balancing correction of the hand, that applying torque to the, what was it, the pivot point of the inverted lever. So stand on one leg and extend both arms out to your side, as like basically mimicking a one arm handstand in straddle on one leg. Then you close your eyes, and as you close your eyes, you will feel that your foot blade will be moving faster to correct the various balance, like you correct your balance, and your legs will wobble more and so on. And this is fine. Now, you are going to do the exact same thing, except you're going to take your arms and hold them overhead. So you kind of grab your hand above your head so that they're together above your head. And then you do the same thing. You stand on one leg and you close your eyes, and just notice how much faster the blade of your foot will have to work. And it'll be very, like, this will be a very direct analogy to the one arm handstand because of that. Like on the foot, since you're so acclimatized to your balance and you're so sensitive to balance on your foot, you will just immediately feel this kind of the quicker oscillation of the foot happening with the legs together over your head. And you will also feel that like the rotation will kind of quicker, or your shoulders might jerk out to the side like quickly, and you need to re-establish very, very fast. So that is kind of like an apt comparison in of those two in relation to these physics.
Just to tell people a bit about physics, though, like this concept of angular momentum and its conservation it's very like, it's all around us basically. It's like the force. No, basically,
shut up,
like
Yoda.
The reason why shut up, Yoda. No, the reason why like the solar system rotates is because the thing that formed the solar system rotated. So like before the solar system was the solar system, it was a cloud of dust. But before that cloud of dust was a cloud of dust, it was like a sun or star that exploded into a supernova. And that sun or star probably rotated, or not probably, it did rotate in the same direction that we rotate. Like the Earth rotates, and the Earth rotates around the sun. So we're like, so the rotation of the Earth is like the conservation of the rotation of the thing that it actually came from. And it's seemed like it's used a lot in physics in the sense that it, like when we describe systems, it allows us to like simplify things and stuff. And it's the same, I guess, in handstands, but you know, for us it's just simplifying calculations. But there was one thing that I when I was thinking about this thing about like, okay, so because people always ask like, what do you do? Like you said before, like, what do you do? You're in a straddle, you start rotating. What should I do? And what did you tell me like a million times, Mikael?
Yeah,
like more down?
leg more down, and just don't allow yourself to fucking rotate. Like, I mean, I would assume in my very limited physics understanding that somehow through this understanding of this code of the one arm handstand, you need to find a way to apply the opposite force somehow to this rotation to be able to stop it.
So the idea is that obviously you shouldn't rotate by like, and then we think about where could the rotation be coming from? Most people would probably not rotate their spine, probably. So it's probably coming from the shoulders. So, you know, locking the shoulder in place. And then that's why kind of, at least recently, I've really liked the idea of like externally rotating the shoulder, at least thinking about it a tiny bit. But one thing I've seen, because there's some people around me here in Iceland that are starting the one arm journeys, and I see a lot of bent legs when they start rotating. Classic. Which technically is, it's very classic. You see it, like people start rotating, and especially if the top leg is going over, they will bend the knee of that leg. That's the thing. And why? Because they just shorten their lever. The rotation. So they're going to rotate faster by doing it, because the thing is like the initial rotation is now bringing their central of mass outside of their base of support. So they're losing the balance. So they're like, oh my God, it's actually going out. I'm going to bend my knee to try and move it back in, which just makes them rotate faster and spin even faster out. But you can obviously save it that way if you're actually falling due to that. But it's very interesting because you see people do it all the time because they don't realize it's rotation. They think it's like a linear fall out of it.
That is something I've actually thought about quite a lot, is that because when like if we're assuming that the pressure from the hand to the hip is rather stable and solid, and you begin falling, let's say you start falling over towards overbalance on a one arm, like I would assume that there, within the statistical probability of you falling directly over, meaning that both points, the outer points of your legs, will start moving backwards at the exact same speed at the same time. It is a possibility, but it's an extremely unlikely one. So what tends to happen then is that like as that overbalance happens, it starts to manifest to us as viewers and as performers of the skill. It manifests as some sort of rotation simply because like there is so little probability of it not starting to rotate as it falls in that direction. But there was also this other thing I was thinking about in terms of if we're thinking about the torque from the hand and the ability to move the shoulder and so on, which then
this kind of gets into the interesting level, the idea of like levers and deformable levers. So you're always making the assumption in physics that your lever can't deform, whereas the human body can deform under force, and force also transmits as a wave. So you're like, I apply force on my fingers, and it takes a while to propagate to the center of mass and make the correction, or provide something to actually do the correction against. So it's kind of...
Is there a way to calculate the speed of that? Like,
what's that?
Is there like, no, that's just a random question out of my ass. Is there a possibility to calculate, like, I apply pressure to the floor with my fingers, how long does it take for that to actually act upon my center of mass? Suffer.
Speed of light? No.
It's one of those ones you can work. I actually looked into this, boom, and we can.
It's more biomechanics,
it's kind of like
right?
You can work it out. You can work it out with a high-speed camera and pressure plates. And they have done it for running and stuff like this. And this is kind of when you get into the areas of like tendon stiffness and how fast tendons will store and transduce force across them. But I don't think it's...
Because if it's just a stick, it's pretty much instantaneous. But we're not sticks. That's the problem.
Yeah, because there's also muscles that will need to tense like up the chain and so on specifically. Yeah, for sure.
Yeah.
Very interesting stuff.
Yeah. It's like we got from fluid-filled, organy, bony sacks to sticks, and now we're back again. Now we're like, well, tell us more about your fluid dynamics and how they work in a simple harmonic motion.
It's... I mean, like you could do this, and especially like the paper that you sent me, Emmet, with this like calculations for the human body. That was an old paper, like ish. But you could do like simulations of this stuff, which would be basically the only way to actually do it. But you could just like simulate it, like how like write a program that calculates all of this for you. It's technically quite simple because it's just Newtonian
the
physics.
correct thing is you could write the program
of a
for
lot
us.
of body parts. Like basically,
I don't think my programming skills are good anymore.
I'll wait till my kids graduate high school.
Do it when they get their PhD.
And then have them do it.
Kids that need your help solve this problem. Right.
Yeah, I feel I have tons of things to think about.
Yeah, I think we're giving a lot of people some stuff to think about. I think we're going to end it on that point because it's, PhysicsCast. So I'm just going to try this out for anyone who has managed to make it this far into the podcast. And hopefully you've got your notebooks out and are doing some equations and want to send them to us. If you have any physics questions or anything else, send them to us on @HandstandFactory or via our contact form on the website. And we'll see if we can get Helgi to answer them for us. Or we can answer them ourselves with our made-up science. Other than that...
I'm sure that this could also be a topic that could come up again at some point in the future. I guess there's quite a lot to delve into here once we start fleshing out the thinking around it.
Yeah. Fingers, a lot of stuff.
It's one of those things I've been working on a bit. I was grabbing out my maths and I was trying to work out the three-dimensional vector forces involved in a one-arm handstand and how we can translate the moment of inertia to the raising a center of mass to the rotation speed, and basically give every handstand a battle rating of like, so you could go like, how hard is this handstand? How hard is it? One. It's actually giving some interesting stuff.
Yeah.
So that's something to look forward to. Coming
in the
soon.
future.
But
coming soon.
I guess it's thank you to the Helgi Freyr, the ultimate life form.
Helgi, if
thank you guys.
Anyone wants to check you out or find out anything more about you, where can they do that?
Mainly on Instagram, Helgi_Freyr. Yeah, that's about it. I run a gym in Iceland called Primal Iceland. We sometimes host these two guys, Emmet and Mikael. They've both been there.
I know they've got like an awesome sauna and like cold tanks.
Yeah.
So good.
So we just come back for that. Iceland's amazing. The gym is awesome. If you ever get a chance and you're one of our listeners, you want to go to Iceland for a bit of a holiday and do some handstands, check out the gym, Primal Iceland. Definitely gets 3 thumbs up.
Yep.
So the funny thing is, like, they're above one of the biggest CrossFits, but like we've never stepped into the CrossFit because Helgi's gym is so good. Not saying the CrossFit is bad; it's obviously one of the best in the world, but Helgi's is just better. Other than that, we're going to wrap up now. We've been Handstand Factory. That's been Helgi, and thank you so much for listening. And speak to you next week.
Cheers.